This video is for modeling a magnetic levitation system, and specifically we are doing this levitation system modeling in MATLAB. We'll be using the MATLAB script, not usually the Python script, and we'll be doing all of the training on some sort of the data that we have received from the ANSYS simulations, and we'll be seeing all of those data also, and we'll be moving on with. So let's just start with what exactly we'll be doing here. Maybe you have heard of the recurrent neural networks and convolutional neural networks. So similarly, we are here having the NARX, that is the non-linear autoregressive with external input neural network. Okay, so what does it do? Let me just describe you in a few sentences. Suppose a network, these network, any RX network can learn to predict one time series given another past values of the same time series, like the feedback input and another time series called the external or exogenous time series. So how this is going to happen and what kind of the data we have. When you do in the simulation in the answers, similarly you are doing the simulation on the track, you are doing the simulation on the velocity, pressure, anything or any type of mechanical simulation that you are doing. So most of the cases what you receive there, that you receive a timestamp and you receive a value of that physics that you are actually simulating, so like velocity or something like that. So similarly what we have here, we have from the Maxwell ANSYS Maxwell, we have generated the data for our magnetic levitation system for the control current and the magnet's position on the specific timestamp. So what this is the problem. So we have the magnet's position, levitated magnet's position, and the control current passed at that timestamp. Okay, so with these two data we'll be predicting the next set of the magnet's position on the next set of the timestamp. So this is what we will be doing today, and that is why we are using the NARX. So we will be building a neural network, NARX neural network, for predicting the dynamic behavior of magnet levitated using a control current. So why do we are using the neural networks? So this is really not a question to ask here. Conventional neural networks has even outperforming the recurrent neural networks, but we are still going with the neural networks. Recurrent ones are similar of that feedback based neural networks here. So what we'll be going first of all with the data, how the data. So let me load the data here. For loading the data, we'll be doing all of the scripting here in here. So it might take, I'm kind of new to here this. So it's auto completion is doing a lot of Maglev underscore data set. So, and we'll be executing it. So execution command. So we have loaded the data. So this is Maglev underscore data set, and X and T that you are saying. X is the row, it's row cell array, and this is the timestamp, associated timestamp with the control current. So we can see this data here from directly from here. So these are the control current being passed, and here you will be seeing around 4000 sample, 4001 samples is there, and the same here the T data. T is also the row cell array, where each element is the associated timestamp of the levitated magnet position, and this would be certainly in mm, where these data are in the mm, and this will be also of the same size like 4001. So now we'll be switching on to again to our script page. Now what we have, we visualize the data 4001 timestamp, 4001 timestamp. Similarly we will be doing here with this uh, MATLAB scripter. Okay, so what we will be seeing, we will be seeing the size of X, and that's what we were executing. Okay, so this is so size of X is 4001, and similarly we will be having here the so this is kind of, and similarly if we are going to insert one more script in here, size of Y, what we are talking, size of T will we see. So size of T is also 4001 and 1 by 2. So now we will be moving on with now modeling with our neural network. So here it is modeling with neural network. Okay, so what we have seen the size of the data set. Now we will be moving modeling with neural network. So for we have to first of all create the neural network that will learn the to model how the magnetic position changes on each of a specific timestamp from the given control current. Okay, for that, since the neural network starts with random initial weights, so first of all, we will be setting some random initial weights. So, what would be the best random initial weight? Let's take example of like current time in millisecond. So, what will be going on? Let's see current time in milliseconds. So, it should be like around. We will be taking around something similar to that. So, okay, getting back here, and we'll be writing a script set random set demo rand stream, and here we'll be passing the I think this is kind of a little longer, but see, this is actually set is non-negative integer, so we have to put it in the integer range. So this would be, I think, it would work. Okay, so we have set the seed for the randomizations of our data set. Now we will be now further we will be getting the model. So for this we have created multiple models, so we will be starting with the two layer, that is one hidden layer in NARX neural networks. And here we have the we will try first of all with a single hidden layer with the 10 neurons inside of it. And we also try using the tap delays with two delays for the external input control current and feedback magnet positions. And more delay will allow the network to model more complex dynamic systems. So the input and output sizes of 0 we will be using because the network has not yet configured to match our input and target data. So so as the network will be trained, we will be here the sizes of the input and output data will be changing. Okay, so now here for this one we will be here inserting a script, and that would be getting the net is equal to NARX net, and we'll be passing the input delay size, that's 1 colon 2, output delay size, feedback delay size, that will be also 1 colon 2, and here the hidden sizes, how many hidden neural networks you want. We are going with the 10, and we will be saying the neural network, that is a view net. Okay, so this is what we are getting the neural network here, 1:2, 1:2 weight bias, and there the hidden layers and 10 neural networks. So this was the view of, and the same view we have also been actually put into this a script. But then we'll be moving on with training part. But before we train, we have to prepare. We must first of all we must use first two timestamps of the external input and feedback timestamps to fill the two tape delay states of the network. Furthermore, we would need to use the feedback series both as an input series and the target series. Okay, so the function here that we'll be using, that pre-parrots, that prepares the time series data for simulation and training for us. So x data will consist of shifted input and target series to be presented to the network, and xi is an initial input delay states, and AI is the layer delay states, but in this case as there are no layer to layer delays, and TS is the shifted feedback series. So what do we have to insert in here? We would be writing here, we will be actually preparing the data sets. So xs, xi, and AI and TS. So its auto completion is kind of, see, let me do this. Yeah. Okay, so prepare nets. We'll be passing here the net x and the tuple and time series. Execute it. So this is preparing the time series data for simulation and training for us, and I think did it run or not? It's ran, and we got all of the values prepared. Now the network is ready to be trained. The timestamps are automatically divided into training, validation, and test sets. So validations and test sets. test we have got AI the validation, and XS XI is the training set. The training set is used to teach the network. Similarly, the training continues as long as the network continues improving on the validation set, and the test set provides a completely independent measures to measure the network model accuracy. So neural network training tool shows the network being trained and the algorithm used to train it. It also displays the training state during the training, and the criteria which stops training will be highlighted in the green. So the buttons at the bottom open useful plots. So we'll be seeing all of those plots here after running the next script on the training. Okay, so which can be opened during after the training, and you can see all of the training graphs, your graphs and all of those to improve your model. Okay, so and see, we have what we have prepared. We prepared the XS, XI, AI, TS. So those all of the data is here has been actually been in the put into the workspace, and you can pretty much see the data how we have modified them. XS, XI, XS and the XI. So these all of are the XI are the initials. So this is 3.575. These are the control current, and this is the timestamp, and the same for the XS. So this is also the control current series, and this is the time stamp series. And what we have the test series. So test series, how many sample we have got in the test. So we have got around pretty much around we have split the data. This is 4,000, more than 4,000. This is 4,000, 3,099. Your 999 is also in the test series. So we'll be again switching back to we'll be doing the training part. So we'll be writing the script for that. That is I will be writing the script. So it's kind of a little so net training train. It's auto completion is kind of tricky. Net X XI, and we have X's the test sets, X indexes, X initials, and AI. That's the validation set, and we will be doing the training. So it will take just a few seconds as the computer being used is quite great, and we are running 1000 epochs, and these are all been taken as the default data. So as you can see here, the training and the epoch numbers improving, and the gradient performance elapsed time. So it's written quite high as like a model stopped being training, so it just moved on with those all of the epochs. So only it's stopped at the 151 epoch. We have gated that 1000 target, but as the network were stopped learning, so it just stopped right up there. Okay, so now we will see here some more of the performance training state errors, and first of all let's go with the performance graph. So this is the performance graph for the training data sets that we had created, validation, test, and best that we have received is being shown as a dotted line at around 10 point. It would be 10 point minus. Maybe you can consider 10 point minus 58 or something. 151 epochs we ran for the, and you can pretty much export this data figure toolbar, and pretty much a file what I have to save as a generate code import data, and we'll be moving all of the training state data set, training state graphs. So this is 151 validation checks and mu gradient, and you can pretty much see these are all the error histogram you can see from here. So this is the error histograms, and similarly we have the highest training error bin instances being considered at the training. There are the 2500 instances being used for the training and the validations. So this is the data set displayed 3000, 2500, 2700 to around 3400 is for the validation, and for the test we have around 3400 to the 4000, and the zero error and the errors is here been considered as the targets minus output. And this is the histogram with 20 bins. Similarly we can see the regression graph. So regression graph here for the training, validation, test, and considering all of the cases. So I don't think so we can actually zoom in somewhere, or we can pretty much zoom in. So if we zoom in, so we can pretty much see the graph here, and I don't think so. Yeah, it's working, but it's not that great. Zoom feature is not that great, so we can pretty much zoom in here in the this part, which is give BTK process. So this one you can see all of the data and line that where these all of the data have been fit. Okay, we'll be moving on to next set of the time series responses. So these were the time series responses. We are pretty much seeing this graph. So and for the report generation, we'll be actually exporting this all of the images out later here auto correlations, and finally we have input cross correlation. And as we have seen earlier, the network diagram, you can even see the network diagram from here. So this was the network diagram that we have trained our model on. Now we will be moving on to next thing, and see this has actually the training has also inserted here a image of the final model being trained and all of the gradient performance and the epoch that it trained. So now to see the network, how the performance during training. So as we have already seen the graphs, you can also pretty much here write some of the scripts to see those all of the graphs, like some of the like plot perform, and we will be passing here the training data, and we'll be executing it and this one. So this is what we are getting here for the best validation performance. So this is the performance model, plot performance, and this is the performance, and this is shown in a log scale in terms of a mean squared error. You can see here the mean squared error and the log scale, and how it has how the model has learned. And the if pods there we have not even specified the learning rate here in anywhere. So this has all been taken as maybe there will be the gradients of the learning rate, or either it has just taken the default learning rate, and similarly usually it goes with 0.000 so now we will be testing the neural network. So for testing the neural network, and as we have used the MSE for training the neural network, so now we can test this with testing data. So we'll be writing some of the script for that. So that is y is equal to net xs xi. This is the validation data here, and perf is equal to msk mean squared error of the net test data and y. So here now we'll be getting the performance, and that would be, did it run or not? Is it running or something? Oh shit, I started from the beginning. I'm so sad. I supposed to start from here, and just move from within control filter features. So I think we should run it again. No, not here. That used to this one. So what it is we just run that this is the training and validation is also getting different. But let's just go with this one, okay? And later we'll be running this one. So y skill performance, and what we are doing. So if we are writing here the performance, so will be so yeah, we are getting this way. So this is not good, it has to print the performance, and it's just like freaking performance is like 2.26 into 10 minus 6. So and its performance is pretty low. It performance has to be a little more better. Maybe we could run the model again, then the performance would be a little more better. But let's so we are not, so let's just do this. I don't think it would take a little more time, because we are pretty much using a lot better system to train our model. And so here now we are at the training stage. Let's just give it a little time. Maybe it would actually do a little better this time. Train a little more better. Performance would have to be around 2.9. So it's the gradient is dropping out. So just see this time. Give it a little more time. So maybe it's 2.06 this time. It would be better than the last one. And let's just see here the comparison. So it's good, it's good. Let's just move on with this data. It's okay. Let's see, and this, oh shit, now we are getting here the performance of 4.34 into 20.7, and the performance had to be around 2.924 into 2.6. So it's better than even the last one that we had earlier. Okay, 4.34 10 minus 7. So we'll moving on with this performance. So now we'll be seeing we can actually the network's response in comparison to the actual magnet position, and that we can even plot. So we'll be plotting that one, that is the plot response. Every this is all of the gas sensitive for sure. So this is what we have, response of output element or output element 1 for time series 1, and output and target data. And I think we seen this graph earlier. Now plot correlation. So correlation that will be plotting, correlation shows the correlation of error at time t and the errors et with over varying legs, and e t plus lag. The center line that we will be getting here on this drawing this graph. So here so e is equal to, maybe you could just write here in the same script both of the thing. Let's just do this plot correlation, plot error correlation, and there subtract. We are not splitting here, we are just writing both of the scripts in the same line. Let's insert it. So this is what we are getting, autocorrelation of error 1 with the correlation and the lag, zero correlation, confidence limit. Similarly, in plot in correlation, plot in error correlation shows the correlation of error with respect to the inputs with varying degrees of lag. In this case, most of all of the lines. So let's just see first of all that one plot in error correlation with test set and xs. That's all of the data that we have not just passed as initial data, and the error. See, earlier what we had to do here, earlier we could just the actually here we had to write this one as of the this one a g subtract as of a new e variable, because we need it right there in the back there. So, and here we are going to have to pass this e value to draw this graph. So this will be the same, but now we will be passing the same data here as the confidence within the confidence limits, and this is what we will be getting here. So this data says here that in this case most or all the lines should fall within the confidence limits, including the center line. Now the network has trained and open in an open loop form where targets were used as the feedback inputs. The network can also be converted into closed loop form where it can where its own predictions become the feedback units. Now what we are going to do here, we are going to create here a closed loop net. So for that, and that closed loop net we will be doing the modeling. So for those we will be start here writing some of the scripts. So already this net 2 is called the closed loop, and we will be saying the net 2 it is executed. So this is what we are getting, the NARX neural network, and this is the closed loop net. So what's here, what we are saying here, the different, there's the hidden and output layer, and similarly xt input and white is output 10, and this is almost of the same, but what we have closed it. So it's going to give the feedback back to the previous network, and Okay, so now we'll be moving on. We can simulate the network in closed loop form. In this case, the network is only given initial initial magnet positions and then must use its own predicted positions recursively to predict new positions. So it's good to when predicting that way. The quickly results in a poor fit between the predicted and the actual response. This will occur even if the model is very good, but it is interesting to see how many steps they match before separating. So again, we'll be using the prepare nets for preparing the time series data, and we'll be taking into account for the altered network that we have altered through the closed loop. So now here we will be actually creating the same axis xi, ai and ts is equal to prepare. Let's net 2. On the net 2 we are going to prepare x tuple and t. Similarly, we are going to do all of them in the same script. Y is equal to net 2 xs xi ai and plot response ts and y. So this is what we are getting. So this actually had work for pairing the data, output and target outputs, response and error. So if this application if the application required us to access the predicted magnet position a timestamp ahead when it actually occurs, we can remove a delay from the network. So at any given time t, and the outputs is an estimate of the position at time t plus 1. So for this we use the closed loop. Now we will be using a remove delay in the first model, first net, and that we will be getting as the net 3 instance, and we will be seeing that net instance. And so this is what we have to. So we will be creating here a net 3 is equal to remove delay net view net 3. And see, we have got here the net 3 model, and what we have the changes from the last net model, that we have removed the delay. Earlier we have been using the delay. First we use the net NARX net, second we use the we closed the loop, and the third we are removing the delay. And we will be here doing the further we will be further again we will be preparing the data set, preparing the time series for simulations with prepare rates, and this time series is the network, again very accurate as it is doing open loop prediction. So but the output is shifted one timestamp ahead. So here we will be here writing some of the scripts. So might be we just copying some of the script from the previous one because it's almost the same thing. And it's just, see, I'm not used to this MATLAB. I'm just doing for this Maglev modeling prediction. So here XSXITS, this is good. Preparedness net 3 will be using, and that we have X, we have triple T, and we will be using going with the net 3 here in this one, plot response TSY. So when execution of this one, this is going to give us the response of output element 1 4 time series 1 output and target data. So now this example illustrates this script illustrates that how to design a neural network that models the behavior of dynamical magnet levitation system. So this was the whole of the magnetic levitation modeling with the Maglev NARX neural network. So this was it. Have a great day, guys. Thank you.